Thank you for coming today. My name is Steve DeCina. I'm the Executive Director of Penn Climate, and it's my pleasure to welcome you to today's seminar. We are excited at Penn Climate to partner with the Penn Institute for Urban Research, Penn IUR, to bring Dorit Aviv from the Weitzman School of Design to our seminar series. Professor Aviv is an assistant professor of architecture at the School of Design and the director of the Thermal Architecture Lab, a cross-disciplinary laboratory working at the intersection of thermodynamics, architecture, and materials science. Her research focuses on developing innovative solutions to some of our most pressing challenges, including cooling, air quality, and energy performance in buildings. What makes Professor Aviv's work so interesting is how she harnesses cutting-edge materials and architectural forms that work with nature rather than against it. Her projects demonstrate that cooling does not have to be energy intensive. We can keep people comfortable while also reducing energy consumption and carbon emissions, which is really cool. Professor Aviv is one of Penn's true innovators. She's developed an evaporative cooling roof chimney for desert climates that uses hydrogel membranes to cool and humidify air, for which she received the Holcim Award for Sustainable Design and Construction. Professor Aviv also previously installed a pilot-cooled bus shelter in North Philly, and earlier this year unveiled the KlimaKover Pavilion on New York Governor's Island, where it was on display for much of the summer, allowing the public to see how membrane-assisted radiant cooling works as a scalable alternative to traditional air conditioning. Professor Aviv holds a PhD in architectural technology and a master's in architecture from Princeton. Her research has been supported by the U.S. Department of Energy, the National Science Foundation, and the National Park Service. She's been published in leading journals and has also been featured in outlets like NPR, Scientific American, and Architectural Record. I'm really looking forward to today's seminar because when I think about that the general public thinks about increasing comfort during extreme heat, they mainly think about air conditioning, which we know is carbon intensive. But as temperatures continue to rise, we must seriously considering alternative cooling methods and explore ways to provide comfort in areas beyond just our homes. Professor Aviv's work not only proves that these alternatives are feasible, but also provides tangible examples of these solutions in the real world, offering comfort to the public. Please join me in welcoming Professor Dorit Aviv.
Hi, everyone. First of all, thanks for having me, Mike and Steve. It's really wonderful to be part of this new initiative at Penn. Super excited. But today I'll talk about things that Steve just introduced, about my work on cooling, both for the indoor environment, for buildings, but also for cities, for the outdoor environment, which more and more I've been actually asked to tackle. Before I start talking about those projects and how they work, I'm going to explain why we even need alternative forms of cooling, and also how cooling is actually at the intersection of two of the most defining environmental health challenges of our time. So I'm going to start with this terrifying image. This is NASA's prediction for the summer of 2100. And what you can see here is that large swaths of the globe are going to experience extreme heat, not just for a few days, for the entire summer. Temperatures that are above 104 Fahrenheit or 40 degrees Celsius. And what does that feel like? Well, we've had many previews of that around the globe in the past few decades. Actually, from 2021, you can see here to the left, one of those heat waves that hit the west of the United States and Canada. And during that June of 2021, basically areas that never really needed air conditioning, like Vancouver and Seattle, all of a sudden experienced this extreme heat wave for a few days straight. And people ran to buy air conditioners. And what happened? peak demand, no one could actually even use the air conditioners they were buying. There were blackouts in the places that suffered from the most extreme conditions, and that ended up causing hundreds of mortalities. So we know that we need cooling because cooling saves lives. But the other side of that is the International Energy Agency is predicting that cooling is the fastest growing energy sector. Well, it is the fastest energy sector. It's actually tripled since the 1990s. It's predicted to triple again in the next 20 years. So what does that mean? The building sector is already has the largest impact out of all the sectors on greenhouse gas emissions globally, right? It's mind-boggling that it's more than industry and it's more than transportation is the energy we consume in buildings. And the majority of that is building operations, and building operations is largely heating and cooling. So if we're going to keep growing this cooling demand because of cooling, basically air conditioning spreading around the globe, we're going to make a big effect. It's not a small one on greenhouse gas emissions. So we're going to still keep contributing to this vicious cycle of us needing cooling and the globe getting warmer. And again, we're going to end up with that summer that we just saw. So we can't keep going this way. We need alternative cooling solutions. What is another environmental health crisis that we've faced just over the past few years other than climate change? The environmental health crisis that's also affecting cooling and buildings that really came to the forefront during the COVID pandemic, which is health in buildings. So the way we design buildings today is basically as these, do I have a pointer here? Yeah, as these sealed boxes. And the way cooling works is there's an air handling unit here, and fresh air comes in and gets circulated to, after being cooled right here by mechanical systems that rely on fossil fuels, into the building. But actually, most of what's coming into the building, most of it is not fresh air. Most of it is recirculated air that's mixed with that fresh air. And the reason to do that is to save energy, right? So we don't need to pre-cool these huge volumes of air. We can save energy, cooling energy like that. And we seal the buildings. We make very tight envelopes. We are in rooms that don't even have operable windows, right? Because everything is controlled centrally. Well, that works until it doesn't work. During the COVID pandemic, this is maybe a graphics that you know maybe from the New York Times. It was on the cover of the New York Times when they were trying to show what happens in a room with closed windows when there's a sick person in the room. Because what we've experienced during COVID is the buildings have become sites of infectious disease spread, right? There were so many more instances of infection indoors versus outdoors. And that's when the governing bodies or the associations that advise codes and standard and governments on building codes around the world came up with these new directions. Stop recirculating air. Go to 100% fresh air into your mechanical systems. Well, we did a study at that time of what that meant for energy, for cooling energy. And you can get an increase of over 200% of cooling energy if you go to fresh air. So again, the problem is really our paradigm of how we design buildings. We're designing buildings in a way that cooling and health or cooling and fresh air go against each other. If you're trying to conserve energy and recirculate air, you're damaging people's health. If you're trying to provide fresh air, then you will have these energy spikes. So this first project that I'm going to show here really tries to tackle that directly. This is an adaptive wind catcher or a variation of that. It's actually a downdraft cooling chimney that we installed in Arizona to test it. And this is for arid or semi-arid climates. Now, what are those climates? Those are actually those, if you think back to the map I showed before, those are some of these climates that are going to experience the hottest summers, because those deserts or semi-deserts are basically the places where temperature is most extreme around the globe. But the other side of that is that they actually provide us with that climate provides us with a lot of opportunities for natural cooling that we can take advantage of. So in this prototype, what we did in this pilot was to combine two cooling technologies that are really based on how that dry, hot climate works. One is evaporative cooling from hydrogel that's embedded. Oh, sorry. Going back. Can I get the pointer to work? Okay, maybe not. But it's embedded in the top of the chimney, and it evaporates passively water into the air, and that humidification of the air instantly cools it down and makes it drop into the building below. And the other technology is radiative sky cooling, where we're reflecting solar radiation with special coating, but allowing for infrared radiation to the sky. So here you can see this prototype that we initially built in the lab. And then you can see here the evaporative downdraft cooling, where the hot, dry air of the desert is pulled in through the evaporation process from the hydrogel membrane that's embedded at the top. You can see here how basically the molecules of water are evaporating into the air, cooling it down and making it denser and heavier. Here you can see us casting the hydrogel membrane. We're preparing the test for this. And with smoke tests, we're actually testing the downdraft. And you can see with the smoke test how the air is dropping down just by coming into contact with the wet hydrogel membrane. The other thing we're doing is embedding thermomass, high thermal capacity materials into the building envelopes and coating it with a reflective coating that reflects solar radiation, but still emissive to the night sky. These are these pockets that are embedded in the envelope. And we've tested different materials for that, phase change materials and hydrogel itself. When you expose this to the night sky, in the desert, the night sky actually drops to below zero to freezing temperature, below 0 Celsius to freezing temperatures. And just through this exposure and exchange between the envelope and the sky, you gain additional cooling. This prototype won a Holcim Award that's an international award for sustainable design and construction in 2021. And what was interesting is that these you can see some of the tests we did for the hydrogel to understand its property as it expands and contracts. But what was interesting is that actually Microsoft saw this prototype and became interested to see if we can apply this to data centers and achieve data center cooling with minimal energy input. We did a whole study for them. This requires a very different scale of cooling because of the density of the heat that's coming out of the machines. But we did find that in certain climates, and this is completely climate dependent, we can actually provide part of the year the amount of cooling that's needed. And this was a model that we did in a collaboration with Paolo Aratia from the engineering school. These are some of the studies we did. Without going into too much detail about that, I just want to go back to the larger point, which is that the goal of that project was to rethink architecture literally outside of the box. In this case, their air handling unit box, right? So how can we think about open architecture that promotes fresh air to come in? Here, the more fresh air you bring into the building, the more cooling you get. So the two go together now, right? So there's not a competition between fresh air and cooling. All right, so that's just an example of one of the projects we do for buildings, for thinking about energy and health in buildings, in building interiors. But if we go back to this map of global climate, this map is very zoomed out, right? It's basically as zoomed out as you can get. And what emerges from it is certain patterns of where are the places that are going to experience the most extreme heat, which climates, which parts of the world are most heat vulnerable. But when you zoom in, you start understanding that not every place within a region experiences the same heat vulnerability. That once you understand differences, local differences, it gives you a very different picture. Here, what you can see is a visualization of satellite data of the heat island effect, right? So cities are much hotter than their surroundings. And this map actually shows you the difference, right? That highlights the difference locally between these cities that we call them heat islands because they become these islands surrounded by cooler temperature, these very hot islands. The reason why this happens is there are many factors affecting that have to do with the way cities are built. They actually are, our streets are creating what we can call thermal canyon, or they're called urban canyons. We can think about it as thermal canyons where solar heat is trapped. It's reflected down into the sidewalk. The sidewalk is on the road. The roads are made out of heat absorbing materials. And we also don't have, for those urban surfaces, there's not a lot of ways to cool themselves once they absorb all the heat because they have very little exposure to that cold sky that I mentioned at night because of the density of urban form. And there's not a lot of wind that can go through those streets. So all of that adds to these higher temperatures, which again, if we look at them, now, zooming in a little bit, we look at these islands, right? This is still on the left. We can still see those cities as islands in satellite view, but we can still zoom in more. And this map to the right is a map for the city of Philadelphia made about hotspots within the city. So within cities themselves, there are neighborhoods that suffer much more extreme heat conditions than others. In this case, you can see here highlighted one of those hotspots, the Hunting Park East Tioga neighborhood in North Philadelphia, which suffers something like 15 Fahrenheit degrees more than other areas for Philadelphia. And that has to do with the history of this investment where these neighborhoods have less parks and less trees in them compared to others, less tree canopy, which has a huge impact on the heat island effect. So when you think about those neighborhoods, there's this compilation of different effects that really put people in risk and make communities there much more vulnerable to heat exposure, right? So these are already neighborhoods that have other issues with environmental health, that have socioeconomic challenges. So we can see here how heat actually creates differences and magnifies existing inequalities. How are cities addressing that? Addressing the fact that some people are in actually, life danger during extreme heat events. And those are maybe the people that don't have access to cooling, or if they have access to cooling, even if they have an air conditioning unit. What we've learned also from this study that the city of Philadelphia did is that sometimes people have to choose between turning on the air conditioner during an extreme heat event and paying, can they pay there for food, right? So those are the type of choices people have to make. How are cities dealing with that? The most common strategy in the US that's been kind of promoted over the past decade, especially because heat waves are becoming more frequent and more extreme, is having cooling centers. And those are existing buildings in the community, or sometimes outside of the community, that become designated cooling centers where people can go during a heat wave and get free cooling. That's like the number one strategy that's like on the Environmental Protection Agency's website, et cetera. And more cities are adopting that. But this strategy has a lot of problems with it. One of them is that it actually relies on massive energy because of air conditioning. So what happens during a heat wave, the grid might shut down, right? You might have a blackout. And then, this is where you need cooling the most. So some of them have backup generators. Those are usually diesel generators. They have other negative and environmental health impacts. Or or sometimes they shut down, especially, for example, during COVID, they shut down because they were not deemed safe. Another problem is that they're just outside of where the community needs them. Because think about it, you need to go to work right now, but you're going to go to a cooling center and you're going to miss work. So how does that really work for you if you're a person that actually needs access to free cooling? So again, working back with the Hunting Park Yoga community through a project that started from the Penn 4C, which is a collaboratory initiative that was started by Penn Engineering and Penn Nursing to work with communities in Philadelphia and find real solutions to them. We started working with an organization in Hunting Park to think about how do we actually address the heat island effect there. And in this survey that the city of Philadelphia has done, as well as in conversations with the North 10 organization, which is a central organization, community organization in Hunting Park, this idea of a cooled bus station came up. Basically, I think probably all of you have been at one point waiting for a bus in Philadelphia. Most bus stops don't have any shelter associated with them. It's just a sign. This is true for this neighborhood. And think about standing in a street for 20 minutes waiting for a bus to go to work or to take your kid to school during an extreme heat wave with no shade, with no trees, right? So that's the condition that they've said they really want to tackle. This is what they really need to be addressed, is to have more street shelters that they can shelter on where they need them, where they have to spend time outdoors to maintain their livelihoods. And what we've done is we've come up with this idea of a bus stop that's cooled not by an air conditioner, because for that you would need to actually build a building, right? You would need to make an architectural enclosure and then cool the volume of, continuously cool a volume of air in it. Here, this is a completely open air bus stop, right? So it lets the breezes in through it. What is cooling you here are the surfaces. So the surface of a person standing here, this person is being cooled by radiant cooling panels around her, and here the seat, the bench of the bus itself is also cooling you. How did we achieve cooling of radiant cooling. What is radiant cooling, and how do these panels work, and how did we achieve them in the very hot and humid Philadelphia summer? Right now we're talking about humid climates, no more dry climates. This is why we also can't use evaporative cooling in this case, because it's just not effective. So we have to think about other ways. So the innovation here comes from a research that I've been part of. This was an international group of researchers from the US and Europe and Asia that came together to build this prototype in Singapore in 2019, where we achieved radiant cooling in a hot and humid climate. And what is radiant cooling is basically the idea that you, instead of cooling the air, you can cool the surfaces around you. So this person is being cooled because there's just chilled water running through tubes, creating a cold surface that's absorbing heat from a person. And if you think about it, it's, just what is this type of cooling? It's similar or opposite to how the sun heats us up. So the sun is heating us, right? We're all intuitively, we understand that the sun is heating us without any relationship to the air, right? This is just about exposure. We stand in the sun and we feel hot. And we know that that the solar radiation is going through outer space, not through air. It has nothing to do with air temperature. Actually, everything, all the surfaces around us are radiating at us, just like the sun is, just at the much lower temperatures. And if we lower the surface of the temperature of the surfaces around us, then our body is really like the sun. It's losing heat to those surfaces and they absorb it from us. So this is great, but what is the challenge? And this is not a new technology either. But what is the challenge of doing that, of cooling surfaces to absorb heat from people in a hot, humid climate? In this case, we built this pavilion in Singapore, which is humid all year round. Okay, this is where I actually turn to you because it's a seminar, right? So I know there's a lot of engineering students in the audience and architecture students too. So can someone tell me what is the problem with cooling surfaces in a hot and humid climate?
They're used to cool the water that goes into the surfaces.
Right, so the energy is actually much, much less than an air conditioner, right? That's the advantage here. That's a very good point to bring up. It's because you're actually cooling water instead of volumes of air, and you can keep that cooling, to a higher temperature. So that is an advantage. What is the problem? Yes, thank you. Let me see. Yeah, we get condensation, right? So in the past, radiant cooling has only been limited to dry environments or to environments that are mechanically dehumidified. And what we did here was to come up with a method to prevent condensation, a very simple method actually, which is just putting a membrane in front of the panel to keep the humid air separate from the cold surface. And while the humid air can't go through, radiation can go through it, because this membrane, like you see in this video here, is infrared transparent. So just like we can see through that glass, because glass is transparent in the visible range, we can see the tree behind it. Our body can see the cold surface and exchange heat with it and lose heat to it in the infrared range, which is what governs our body radiation and all of the surfaces around us on Earth. So that actually allows us to, again, going maybe back to that image, to do this completely open air pavilion in a hot and humid climate like Singapore without getting condensation. And we did a study of what would that mean globally for energy savings around the world. And the fact that you can just, in buildings even, open the window and still provide people cooling, but enjoy breezes as well. And you don't need to control everything centrally, and seal buildings can have huge energy benefits. So this is a technology that then we apply to this idea of a bus stop in Philadelphia as part of the Penn 4C project. And we worked with a nursing school and engineering school on this. Great to see Mark here, who has been part of that. And you can see here these two technologies that we've worked on: conductive cooling from the bench and radiative cooling from the panels. Then we built it. This whole process was done together with the community, together with the North 10 organization at Hunting Park, Cuyahoga. We worked with them on the design. They were part of the construction. And then we tested it together with them and got community feedback on it. Here you can see us doing just that. I'll play a short video about that. The heat island effect is a phenomenon where we have cities or urban areas that are hotter than their surroundings. And there are multiple reasons for that. It's basically how we build cities. It's the fact that we have much less vegetation in cities, that we have a lot of heat-absorbing materials like concrete and asphalt, and that we design cities with urban canyons that really trap heat in them. So Penn 4C has created this collaboration with the North 10 community at Hunting Park, and we've been getting feedback from them and working on developing this cooling shelter, and we're testing it at their facility and getting feedback from community members on this pilot structure.
North 10 is an organization that was founded by our founder, Chase Limfast, some years ago. And he decided that he wanted to go in a neighborhood that was really underserved and left abandoned. So really our pillars are economic development, it is education, because our children are here all year round. It is health and wellness. We're building a community health center. And as always, it's making sure that the people at the heart of what we do. So we know that heat islands are issues around the city. Unfortunately, right here where we serve in the East Tioga area, it gets hotter here in the summertime than other areas. So we decided, why not create something where people can comfortably sit and be outside, but the heat won't bother them because it affects their health. So this is how we came up with the idea of a cooling station.
So there's a few components to that, how this is actually providing cooling. First, simply the fact that it's shading you from the sun. So that's already a huge benefit. Then the bench is actually cooling a bench, which means the surface is cooled by pipes that are embedded in it. And those pipes are being cooled with the heat pump that is powered by the solar panels that are on the roof of this. So your body is directly losing heat to the surface of the bench rather than to the air around you. The other way we're doing it is if you're in a standing position, over there we have those radiant cooling panels. Those you don't have to touch, you just stand, and the fact that you're exposed to them means your body is losing heat to them through infrared radiation. In this specific design, we're combining these different technologies together, and everything is energy autonomous. You don't need any external energy source because basically it works when there's sun, and that's when you need it, right? So the solar panels provide you the energy exactly when you need cooling, which is during the time the sun is really intense.
At an individual level, there can be health impacts. So if you have chronic illnesses, for example, cardiovascular illnesses that are exacerbated by being exposed to heat for long amounts of time, that can be worsened if you live in a heat island, or if you are exposed to heat waves and don't have relief in your home for longer amounts of time. If you have asthma or other things that might be exacerbated in the context of heat for long periods of time, you too might be more vulnerable at an individual level. There are also public health issues that are exacerbated by heat. So for example, there are associations between higher heat and firearm crime and violence, which are sort of other larger public health problems.
My background is public health, and we realize that very disadvantaged communities of color are always the ones that have all these inequities, and part of that issue is health inequities, right? As we know, which you may not know, this area has one of the highest asthma rates among youth, right? African American men lose their limbs more than other race. This is the highest district that we're living in, right? So we kind of look at the social determinant of health model that says people are not healthy because of all these reasons. So we need to work hard to see how can we push back on the determinants. So my hope is that this project will be another opportunity, even if it's just as simple as sitting in a cool space, to make sure that someone is feeling safe and they're feeling better. When you feel better, your health is better.
Yeah, you just saw Sarah Jacobi from nursing school also talking in the video, and she was an important partner on this. She actually conducted with her students the surveys to the community, and we're working on publishing the results for that, really showing that this open air shelter provided significant heat stress relief. Just maybe emphasizing, you can see like a little bit of the panel still here to the right, is that, Philadelphia summer is actually is hotter and more humid than Singapore is, right? So Singapore is hot and humid year long, but Philadelphia summer, and we've all experienced this, is very hot and very humid and getting hotter. So what happens is that the dew point, right? That's the temperature at which the air condenses, that it becomes water, and then that's the reason we can't do surface cooling usually. It can be very high, right? So sometimes it's up in the 80s. You need those surfaces to be much below that in order to extract enough heat from the human body to get enough heat stress, right? Relief. So that's what the membrane is doing, is it's allowing you to get more heat out of people by allowing you to do radiant cooling below the dew point. So we kept working on this idea, and now like trying to think about, can we scale it up beyond, like a shelter that's the size of a bus stop? Can we create a modular structure that's maybe adaptable to different conditions, to different urban needs? Like when a cooling center shuts down, can we have something mobile and expandable that can go and provide necessary cooling during those events there? And I think, an important part of it is that this is solar powered, right? So we don't need connection to the grid. So we tested this in a recent collaboration with different collaborators, including Henning Larsen, architecture firm in New York, and AIL Research. And we did exactly that. We tried to build an expandable modular cooling shelter that also people would like to be in. And we created we installed this new type of radiant cooling panels. It's actually transparent or translucent. There's water running right here. And that's what's providing you cooling. And the water is coming in from the top. I'll show in a second pictures of exactly, of what that looks like when it's built. But the idea here is that you create cooling just by using these translucent panels, and that everything is solar powered, and you can build it and expand it as you need. And we're testing here the impact that those panels have on heat stress. How many degrees can we lower the radiant temperature, the temperature that really affects heat stress in the urban environment? And we can do that by over 30 degrees Fahrenheit. So this is the realization of that. We actually built the first publicly accessible radiant cooling shelter that's completely solar powered in New York City this summer on Governor's Island. You can see those panels as they are built here. This is like the big team that really was needed to make this happen, including just permits to do this new technology in New York City. But we did make it happen, and here we're testing, and you can see how much cooler the panels are versus other surfaces. And we're augmenting that effect of cooling by adding some panels that consume no energy, the reflective ones. And they really work like infrared mirrors, right? So if you think about if you had light and you had a mirror, or even just a white surface, right? We all know that if you have light shining on a white surface, that it would reflect light in the room and magnify the impact of light. Here we're doing it with material, which is in this case reflective mylar that reflects really well infrared radiation. So we have just a few cooling panels that are active and consume energy, and they are connected to the chiller that can be chilled down with the solar panels above the roof. And again, that's kind of the gradient of temperature that you're experiencing, and the experience is very different than walking into an air-conditioned room. So part of the issues that we have as a society is that we're so locked on cooling equals air conditioning. This, part of why it was so important for us to have this new type of publicly accessible cooling shelter open to the public in a central spot is that people can experience what it means to be cooled by a surface rather than by the air around us. That's us actually testing that in the launch of this shelter. So we're actually working now with additional communities, both in the United States and actually outside of the United States, around the world, that need this type of technology to expand its reach. We also work, and I'll be I think I'm running out of time, so I'll be quick with this last part of my presentation, which is about other work we're doing with communities in Philadelphia. Thanks to a collaboration with Russell Composto here and his lab, we became involved in helping the city of Philadelphia assess how urban surfaces can be impacted with reflective coatings. How would that affect the surface longevity, but also human comfort? In order to measure that, those are not magic solutions to heat island effect. It's actually, the effect of those coatings is very complex. Doing, for example, reflective coating on a roofs at scale is very positive because you're reflecting all that solar radiation back into the atmosphere instead of it being absorbed into buildings, and a lot of that waste heat goes into the urban environment. But here you're basically, where you're reflecting the heat, you might be reflecting it on people walking around. So it's not that straightforward. In order to assess its effect, we need precise tools that can measure and characterize radiant heat. And that's why Professor Composto brought us in, so the Thermal Architecture Lab has been collaborating on that for the past almost a year to assess over time the effect of this. We're also, thanks to an Environmental Protection Agency grant, we're collaborating with the Netter Center for Community Collaboration at Penn on working with high school students on assessing and mediating heat stress in public schools. Here you can see a project that we did also with Penn Praxis, which is part of the Weitzman School of Design, to measure the heat island effect within a courtyard, in this case, a West Philadelphia school, that really you can see the courtyard is a heat island because it traps heat in it. It's all paved with asphalt and turf, and the surface has become so hot and radiating at people. There was a project with the landscape school, with the landscape department, to create shade and vegetation in that courtyard. And then together with the high school students in that high school and others in West Philadelphia, we measured over this past summer how different courtyards are functioning, both like in terms of heat and health and and air quality. Here you can see my student Yunqing Yu, who is actually teaching high school students how to measure and assess the thermal environment around them. We also did work with other schools in West Philadelphia to look at indoor environments and how classrooms are affected by both heat and CO2 levels when you open or close the windows. It all goes back to this point of we have to start rethinking how we cool building, and we have to start thinking about fresh air and cooling together. And maybe some of these technologies that I've been showing, including the radiant cooling, when you're decoupling the air from basically when you're decoupling air from breathing from the way you provide cooling, you can actually open the windows, just enjoy fresh air, enjoy the breeze, and your surfaces are cooling you. That opens up a whole other future for cooling. And I'd like to then maybe just end with this image that we've been asked to provide for a book about architecture or the city after COVID, and rethinking, what could buildings be in a future where buildings are breathing and surfaces are cooling us. And this was, we try, the language here I kind of adopted from my past as an architect working with someone that had these futuristic ideas about rebuilding society after the war as well. And before I open it up to question, I just want to thank all the amazing students that I get to work with at the Thermal Architecture Lab. The work was, all of this work would not be possible without them. And thank you.